Okay, hopefully you guys had a good break. We're ready to get started with the next session right now. So this session is Applications 1, so it's applications of Charm++. The first speaker is Sam White. Sam White is a third-year PhD student in PPL, and he mostly works on adaptive MPI, and that's what he's going to be talking about today. So without further ado, please.
Okay, I'm Sam White, and as Ronak said, I'll be talking about adaptive MPI and some uses of it that we have going on now in PPL, as well as some outside collaborators. So the motivation behind AMPI, adaptive MPI, is that variability is becoming a problem for more and more applications. So in the Charm++ world, we've seen this for many years now, that software itself has to become more adaptive in order to scale to the kinds of problems that we want to solve. So that can look like multi-scale applications, adaptive mesh refinements, or particle movements commonly. But something we're seeing more recently now is adaptivity in the hardware and variability in things such as power budgets or heterogeneity. And the question naturally arises then, who should be responsible for alleviating the effects of variability in applications and as well in hardware? And some people will say that they can do it all in their application, and other groups, such as ours, think that it should be the responsibility of the runtime. There's also a question of whether there should be a new language for this or whether you can do it in a library. And so our group's answer has been that Charm++ will provide the adaptive runtime system. And then if you have to interoperate with some existing code, we can do that with MPI or OpenMP to work along with existing libraries and reuse those. But another answer to that is to actually re-implement the MPI standard on top of Charm++. And so that's what AMPI is. And the question naturally arises, why would we want to do this exactly? Well, it's to take advantage of all of the different benefits that Charm++ gives in existing codes that are already written in MPI and have already been validated and tested for many years. And so you don't have to actually rewrite your codes to do this. And running on top of AMPI, you can get overdecomposition, latency tolerance, and do dynamic load balancing and fault tolerance. So AMPI is an implementation of MPI 2.2 standard. And the way it works is that we implement MPI ranks, which are traditionally processes, operating system processes. We implement them as lightweight user-level threads. And these threads are actually migratable between different address spaces of a system. So we can virtualize these and run with multiple ranks on a single processor. And we can also run in Charm's SMP mode, where we have one process across a whole node, and we have multiple ranks on each core, multiple cores in each node. So the first key to utilizing AMPI is to virtualize the ranks. This looks like, to an AMPI programmer, just another command line option. So when you launch your job, as well as giving it the number of processors you want to run on, you also give it the number of virtual processors. And then you can do all sorts of things you want to do to map these however you want to the cores of your system. The benefits of this are better cache utilization. As you overdecompose, naturally the working set of each rank becomes smaller. And then you can also schedule these different ranks based on the availability of messages over the network to best overlap communication with computation. One issue that comes up in AMPI and has historically been a bit of a barrier to adoption is that when we take a common program written in MPI, such as this, where we just have the rank and the size as global variables, and then we're going to set the rank for each process, and then based on that do a send or a receive. A problem that comes up when you use AMPI is that we virtualize the ranks inside of a process. And once you've done this, since global variables are defined at the level of an operating system process, all of your threads or ranks now suddenly share the same set of global variables. So in this example here, the first rank will come along and it will set the rank to 0, and then the next one might come along and set that same rank variable to 1. And depending on the interleaving of their executions, you can end up with deadlock here, where rank 0 thinks it's rank 1 because of the race in the access to the global variables. And we've proposed a few different ways to overcome this. So the first and sort of most manual method is to just refactor your code to not use global or static variables. Obviously, this is prohibitive to large existing applications. We've done this for a few of them. I'll be talking about one of these codes later, which is a large Fortran 90 application. And we basically just rewrote the application to eliminate the use of those globals. Another method is to actually rely on the fact that you're running on a system that supports the ELF binary format. And you can actually rewrite the global offset table at the process level every time you switch between AMPI ranks that are executing on the same core. This has a bit of an overhead in proportion to the number of global variables. So if you have many thousands of global variables, that can become expensive. And another limitation of this method is that it doesn't work on static variables, because those aren't defined in the same section of the binary that's visible and accessed through the global offset table. So we've pursued a third approach, which is to use thread local storage. And we ship our own implementation of TLS with AMPI, where we copy out and we switch the offset pointer that's used to access TLS variables during context switch time. And so this method is nicer in that there's only one pointer to update at the context switch, so it's very fast. The limitation is that currently we have to go through and tag all of the global variables with the thread local or underscore thread attribute, as well as in addition to the OpenMP thread private. A different approach that we're pursuing now is to have the compiler actually do that for us. So if you look at the documentation for the Intel compiler, they already have support for something called MPC, which is another kind of threaded MPI implementation. And what they've done is that they've built in support in the compiler where they'll automatically tag all of the mutable global variables with the thread local attribute, basically. So we're currently implementing the back end to that, and hope that we can pursue that in other compilers as well to automate the transformation of MPI programs to run on AMPI. So this is a figure you saw in Sanjay's opening talk, but it's sort of used to explain the message-driven execution model. And here we're just showing that instead of having these chars, each char has a user-level thread associated with it, and the same sort of runtime location management is done, where when we send the message across the network, the runtime will route it to the proper destination core, and sometime later that object will run. Migratability is sort of the third key aspect of AMPI's execution model, and that all AMPI ranks are made migratable between the different address spaces of a system at runtime. So this includes the user-level thread and all of its heap data. The way we do this is through something called the isomalloc memory allocator. You just link in with your application -memory isomalloc. And the way it works is we reserve in the global virtual memory a slot for every single thread, stack, and heap data. And whenever we migrate, we migrate the data to the same exact slot in the virtual memory, and none of the pointers are changed, and everything still works transparently on the other side. So this is quite nice. In Charm++, you have to write pup routines for all of your application's data. But in AMPI, since we're using threads, we can transport the stack along with that and all of the heap data like this. And we don't have to write any application-specific code. Like I said before, since AMPI ranks are implemented as char array objects, AMPI can do dynamic load balancing the same way that charm++ programs do. And so this includes measurement-based dynamic load balancing. You can use all the same strategies that are available in charm++ on AMPI programs. And we also support checkpointing to file or in memory for online fault recovery. And there's basically just one extension method that we provide, AMPI migrate, and then you can pass it flags for different things, whether you want to do checkpointing or load balancing. So next I'm going to talk about a few different applications that we've looked at for using AMPI recently. In work with Abhinav Batelli and Nikhil Jain at Lawrence Livermore National Lab, we've looked at the completeness of AMPI and its performance on a number of benchmarks and libraries. And then we've tried to show some of its benefits to different applications. So the first code that we looked at was a mini app for Monte Carlo transport. And it's called Quicksilver. It's a newer mini app. And we just wanted to compare the performance of AMPI without virtualization versus a native MPI. So this is on an InfiniBand cluster. We've built charm and AMPI on top of its verbs network layer. And the performance is indistinguishable from the native MPI in this system for this application. Next, we looked at Hyper, the solvers library developed at Livermore, and we wanted to compare for different solvers and on different machines the performance of AMPI versus native MPIs. The first thing we looked at was running on a BlueGene system, Vulkan there, and we were a bit surprised to see that for one of the benchmarks, AMPI performed much worse than the native MPI. For other benchmarks, we saw the performance was, again, indistinguishable, essentially, from the MPI and AMPI. But looking further at this, we saw that there were a few different opportunities to improve the performance. We ended up bringing it down about 10%. But what we really realized was that the SMG solver was using a lot of zero-size messages, and the latency that we have over the native MPI here was just killing us. And we confirmed this by looking at a different machine, and on Quartz, which is a new OmniPath interconnect system at Livermore, the same benchmark running on this different system, we actually beat the native MPI implementation there, which was in VAPitch 2. And this is running without overdecomposition. So the thing that we're seeing here is that our all-reduce implementation is actually more efficient than the VAPitch 2 implementation. And the other benchmarks were all pretty much still within 1 or 2%. The next application that we looked at was Lulesh, which is a proxy application for shock hydrodynamics on a 3-dimensional unstructured mesh. And what we wanted to study was how the high-level features of AMPI perform on this application. And the reason we chose Lulesh is that it has different knobs for load and balance. And so the first thing we looked at was how the level of overdecomposition affects performance. And so we ran on Quartz against the native MPI implementation, as well as AMPI without virtualization, and then a number of different ratios up to 1,000 ranks per core here. And we can see the performance is pretty good. Up until the best is actually 64 ranks per core. And you can see once you get past that, up to 125 or 1,000, you start seeing the overheads associated with that high level of virtualization. Next, we looked at the load and balance in Lulesh. There's a couple different runtime parameters you can specify for it to basically arbitrarily create some sort of load and balance that mimics what a multi-material run would look like in this domain. And so what we did is we ran, again, with multiple different levels of virtualization. And we ran with a couple different strategies. All of these results are using Refine LB, since those gave us the best performance. And we saw that the best performance overall was attained with 125 ranks per core plus load balancing. And we actually get some pretty impressive speedups, almost 4 times better in the best case than the native MPI, which is not doing any load balancing. The next application we're going to look at is something called Harm3D. It's a collaboration we've worked on through NCSA and a paid project here with Professor of Astrophysics at the University of Tulsa, Scott Noble. Harm3D is used to simulate and visualize the anatomy of black hole accretions. And it does so through ideal magnetohydrodynamics simulations. This code has been developed over a number of years by Scott Noble, and it's written in C and parallelized via domain decomposition through MPI. The problem that they were looking at scaling up and realized they were going to need load balancing for was this simulation of 2 different black holes sort of revolving around each other in the domain. And so the interesting thing here is that in the inner zones here, there's 2 times as much computation per grid point as there is in the near zone, which is the space surrounding. And in the buffer zone, which is the ring immediately surrounding the black hole, there's 3 times as much computation. And so since these rotate around, revolve around through the domain, it's a difficult problem to balance. And so we've been working with them. They've been doing most of the development on this project externally from us. And it's sort of a new thing for us to have external users of AMPI that don't need as much sort of hands-on attention or guidance from us. But it's been exciting to see their progress. And they're using the TLS globals method where they've gone through and tagged the global variables in their application. And now they've just started recently doing actual runs with load balancing. So this is a very recent result, and this is only on a single node of Blue Waters. But already, just on the 32 cores of a node, you can see the load imbalance arising as an issue here. And we get like 20%, close to 20% speed up. The third application I'm going to talk about today is PlasComCM, which is the main simulation code of the XPAC Center, which is here at UIUC. And this is an NNSA-funded PSAP2 center based on doing plasma-coupled combustion simulations. And so the problem that we're looking at here is essentially modeling a jet engine where we have this turbulent flow, and then we have a fuel source and an ignition point here. And here in the close-up, there's a laser-induced breakdown that leads to the ignition. And what they're most interested in predicting is what the conditions are to produce an ignition. And so one of the unique characteristics of XPAC among PSAP2 centers is that we're not pursuing a new language or DSL. And so XPAC's sort of philosophy is something they call the golden copy approach. And this is that we're taking an existing code that's written in Fortran 90 and MPI, and we're writing software tools that then reuse those standard interfaces to scale the code up. And so AMPI naturally sort of fits into this philosophy where we're not rewriting the application in Charm, we're just going to reuse the existing MPI in the code. And this way, computational scientists don't have to go and learn a new DSL. They already know Fortran and MPI, and they can continue to do their work that way. And so there's a number of different tools that fit into the center in this way. One is a JIT compiler, and another is a tool for source-to-source transformations. So most of these are loop-level transformations to the code. Something that's come up in the center more recently is the fact that we have all these different timescales involved in a single simulation. So for something they like to model is the electrode aging of the aging of the actual electrode that they're using for ignition. But then all of the chemistry and kinetics are happening on nanosecond or, nanosecond scales or microsecond scales. And so something that they are interested in is using multi-rate time integration to only integrate as needed, similar to what Mike was talking about for different galaxies, only time stepping is needed. Here, there's no reason to couple all of these different scales together. And they can actually do less computational work by using different time scales. But naturally, this creates load imbalance where you have different parts of your simulation evolving at different speeds. For PlasComCM, the code is built around this idea of overset grids, where we're using 3 different grids for this particular problem. And the way that the multi-rate time integration is going to work is that we assign different speeds to the different grids, and each rank only owns points on one of those grids. So if we run this simulation on MPI without any overdecomposition or load balancing, what we see is that the 80 years, this is on 128 cores here. The PEs are on the y-axis, and time is on the x-axis. The 80 or so grids that own points on the fast grid have much more work to do than the points in the slow grid. And so we end up seeing these knock-on effects where some processes are waiting on communication on the network a lot more than others. So the way that we want to deal with this in the center is we don't want to have to, again, we don't want to have all of our domain scientists learn Charm++ and learn all of its balancing strategies and everything about that. And so one thing we've pursued is to let the runtime decide when to actually do load balancing and how to best do it. And this way, like I said, the scientists don't have to know the intricacies of AMPI. And so Kavita will be presenting later today about MetaBalancer, so I won't go into much detail about it. But essentially, we're going to use machine learning over the different parameters that the load balancing database accrues. So these are things such as the average load on a PE, how fast that load is changing over time, how many PEs you're running on, how fast the network is, and how much memory there is per char. And based on all of these different metrics, the runtime can actually learn over time while the simulation is going on how to best redistribute the load. And so what we have here at the bottom is a simulation run on 128 cores of Quartz, where we show different ratios of overdecomposition, 1, 2, 4, and 8. And when we do have overdecomposition, we show the results of MetaBalancer for load balancing on those different runs. So all of these are normalized to 1, where 1 is the fastest time step. And you see, without any load balancing, we perform up to 15% worse than the best load balancing strategy. And what we show on the right here is out of the 6 strategies that were considered by MetaBalancer, which one it actually ended up invoking during the run. And so on all 3 of these, MetaBalancer chose greedy LB as what it thought would be the best performing. On the third one, with 8 times overdecomposition, Scotch LB, which takes into account the communication graph, actually performed best. But we were within 3% of that with greedy LB. So we didn't choose the best one, but we still chose one of the best strategies. And so the consequence of this is that domain scientists don't have to know the details. We can do a pretty good job based just on the load balancing database and learning over that. To conclude my talk, I'm just going to talk a little bit about AMPI recent work and what we're moving towards in the future. So right now, AMPI supports the MPI 2.2 standard. We've already implemented support for non-blocking collectives and neighborhood collectives from MPI 3.1. We're moving more towards MPI 3 shared memory extensions. And we've gone back and implemented parts of the 2.2 standard that we were missing, such as user-defined reductions that are non-commutative, and all the complexity of handling derived data types in MPI for collectives and reductions and everything. Something we've worked on is more efficient all reduce and all gather implementations, and attaining more overlap in our implementations of MPI's multiple completion routines, such as the wait and test all routines. Something that's been really big for AMPI is the development of new Charm++ zero-copy RDMA send APIs. In Charm right now, up until 6.8.0, if you invoke an entry method using parameter marshalling, the runtime would make a copy of the array that you're sending, and then it would send them out. But with the addition of the new RDMA send API, you can send things in place without having to make that extra copy. And then you basically pass a callback to that routine as well that the runtime will then invoke when it's safe to reuse that array. And so this allows us to cut down on the memory pressure inside of AMPI and do more efficient transfers of large messages. So in summary, AMPI can provide the high-level features of Charm++, such as overdecomposition and load balancing. But it can still allow users to take codes that are already written in MPI and run them on this runtime. So there's a lot of information in the AMPI manual if people are interested in learning more, and we're always looking for new applications too.
Okay, thanks for that. Are there any questions?
For the automated global determination extension that you're writing, does it just say any variable with external linkage is suddenly a global variable?
For the TLS global strategy is what you're referring to?
You said you were writing a compiler extension similar to the one that's in the Intel compiler?
Yeah, we're implementing the backend to the Intel compiler support. And then we're going to be looking at also extending that to other compilers, such as Clang and GCC. But no, they don't treat anything externally linked in as global variables. You'll have to compile everything, all the libraries that you use, basically with that compiler.
Okay.
I don't think so.
Sorry, go ahead.
I just turned on.
The zero copy RDMA, the stuff that you just talked about, does that work on user-defined types or any kind of types, or how?
So right now it's going to work on arrays and contiguous memory only.
So it's basically a pointer you take?
Yeah.
Is that how it works right now? Okay.
And you can pass multiple arrays to the same entry method, and it will do multiple RDMA operations underneath for those.
Thanks.
We might have I think we'll have a little bit more on that in a talk about 6.8 features, and then possibly in the tutorial on Wednesday.
Thank you.
Okay, let's thank the speaker one more time.